Here's in the news. New exotic matter particle known as the Tetraquark was discovered.
Tetraquark. What do we got in the Tetraquark?
It's a new particle they say they discovered. Okay?
Do I have to read this?
Yeah, go ahead if you want.
Today, the LHCb experiment at CERN is presenting a new discovery at the European Physical Society Conference on High Energy Physics.
Yeah.
The new particle discovered by LHCb, labeled as something, is a tetraquark, an exotic hadron containing 2 quarks and 2 antiquarks. It is the longest-lived exotic matter particle ever discovered, and the first to contain 2 heavy quarks and 2 light antiquarks.
Yeah, it's we're full
amazing.
of quarks. I think the people who are quarks are the people at CERN. They're very quarky, you know.
Hold on, real quick. Just from a layman's point of view, I thought quark and anti-quark. Anytime you have thing and anti-thing, if they're next to each other, they negate each other.
They annihilate.
Yeah. So aren't they breaking their own rules? Off the bat?
Oh, come on! They never break their rules.
Okay, but off the bat, like that would be my first question. I wish we had the guy who did that here, so I could ask him the questions.
They come. I mean, my question is, what sense does it continue to make for these people just to discover new particles? So we discover a new particle, and then a new particle, and then all we do is just name new particles. And it's like I'm going to say really at the end that we don't know what these particles look like. I'm not saying that. I mean, I do, but it's going to be Sabine Hossenfelder who's going to speak for us there. And what she says is that we can't see these particles. We've never seen these particles. So we don't see these particles. We see a trace of something, and we don't see the particle or the thing that made the trace. What we see is the hole through the gas. Okay, we see a trace in the gas, and we say, oh, that was made by a particle.
Calling it a trace is also kind of, what do you call it?
Yeah, you're making a lot of assumptions.
It's leading the witness kind of like was it a trace or was it like a whip that hit it?
Yeah,
there's a lot of things it could be.
Right. And so
it might just be one thing.
And they've only considered traces. They say we're looking at traces. I'm saying if that's true, it'd be very easy to put your ruler across the picture that you've taken, right, and know the diameter of that particle, right? Because if the trace is made by a particle, at least you've got the diameter. And they say these particles are zero-dimensional, point particles. So what the hell are they talking about if they say particle, and here they have a trace, and
it's got at least three dimensions.
They should be at least be able to put the ruler across that. That's simple. I can do that, you know.
That's one. I don't know about the other 2 dimensions, but at least has the width.
Yeah, you got at least the diameter of the particle. And if you got a gazillions of these, just put your ruler on each one. You'll say, okay, the muon has so much, microns or nanometers. You measure, you put the values, and they say all these particles are 0D.
I really wonder how it must be to be a guy working at CERN doing this stuff. Like, are they excited to go to work, or is it just like another thing to give name to?
It's what I used to do in a way. We had what is called implanters at Advanced Micro Devices, all these semiconductor companies, and you accelerate particles, or so they think they're doing that. Okay, and in our case, we accelerated not hadrons or electrons. What we accelerated were ions. Okay, big ions. We weren't doing like a hydrogen ion. No, we were doing phosphorus or boron. Okay, we were accelerating those and bombarding the wafers with those ions. Okay, fine. The question is, we went every day, and what did we talk about? We talked about energy. Okay, we had the KeV. I worked at the KeV, kilo electron volt. These guys work at the giga and tera electron volt. I was very simple, but the mechanism is the same. It's just that I worked at the kilo electron volt, but the whole process is the same thing. You accelerate and you look at what is the energy. Well, this is the energy, and this was the mass. We talked in those terms. Those are the words we used. Okay, but when you say, well, how big is the particle? We never asked that question. We never went in there. How big is the phosphorus atom? I mean, nobody cared about that. We just said, what is your energy? Oh, your energy is too low. That's why it didn't work right. So raise your energy. That's what.
Well, you were also trying to produce a result, so you didn't need to know.
Well, these people, in a way,
they don't have to produce a result.
Okay, but
that's a big difference.
In a way, yeah, but see, in a way, what they want to look at is the result in their gas chamber, in their bubble chamber. They want to look at what happens inside that region where they can map. Okay, they actually do it with computers. It's not like there's a guy with a snapshot there, taking pictures. No,
you missed it. Try it again.
No, they do it with computers because it's just too fast, and they treat everything. The computer's already programmed to treat everything as a particle and as a trace. So no surprise there. Hey, we found a new particle. Yeah, because you called it a particle because you already programmed your computer that it's a particle. Okay, so every blip is a particle. They don't know what that blip is, but they just call it a particle. And so, yeah, they go to work and they accelerate all this stuff. but they never see the thing that they're accelerating, assuming they're accelerating something. Okay, all they do is just play around with the energy. They look at the traces and they say, oh, this one's different. I'm going to call this one Charlie, and the other one's Johnny, and this one's Tommy. That's all it is, and it's just naming new stuff and getting their names in lights, because they play around with the energy, and if they increase the energy, the force, whatever, the mass, the charge, well, what happens, they get a different result, and they say, oh, I've never seen that line before. I'm going to call this one Charlie. That's all it is. And so it's just naming traces. And have they ever shown a picture of any of it in their papers? They say, we discovered a new particle. Okay, what does it look like? It looks like this. See, here it is. It's beautiful. It's red. It's got little pointers on the outside. You never see a particle. All they do is give you the equation. They say this is so much mass, this is so much charge. That's it. And that's why they say it's a different particle, because it's got different charge or mass or whatever than the particle they discovered 10 years ago.
Okay, but when they have news like this, great,
Great
super
news.
quark news, like who gets excited over this stuff? Or is it just to give the science reporter something to write?
In a way, it is just that, because let me tell you something. Any technology is made with anything atom or above. You don't make things with subatomic particles. Okay, that's the first one. And then all they're trying to do is they're trying to understand that secret world, but they're not trying to really explain it. What they're trying to do is they say, oh, we discovered this new particle, this new thing. And why? Because all they can do is describe it in terms of energy, charge, mass, all these mathematical concepts. But have they seen a particle? Do they know it's a particle? No, they don't. Especially when they tell you it's zero dimensional, they're point particles, elementary particles, fundamental particles, whatever word they use. They're talking about a nothing, a non-existing entity that made a trace. Okay, let's move on here. Another in the news.
Am I reading this one too?
Yeah, go ahead if you want, but hold on, let me get this higher.
A new spin on planet formation mysteries. These spin measurements are consistent with the picture of magnetic braking, regulating the spins of gas giant planets during the planet formation process. When combining these rotation measurements with literature rotation measurements of substellar companions as well as our solar system gas giants, we found a tentative trend of increasing rotation rate with decreasing planet mass that could point to magnetic braking being less efficient for lower mass planets. What are they saying?
Okay, what
Didn't get any of that.
what they're talking about is the following. They're trying to explain, how planets form, and they're not talking about little tiny planets like Mercury or even Earth. They're talking about macro planets like Jupiter and Saturn, and even bigger ones that really are small stars that never got to ignite.
But we're talking about the spin of the planet?
Yeah, and they're saying that between the study of their magnetism, the magnetic field, and their spin, they're looking at all these parameters and they're trying to figure out how these planets form, because they're trying to figure out how Jupiter formed, essentially, or confirm that it's through this nebular hypothesis version of planet formation.
The nebular hypothesis being that atoms just keep coming.
No, it's think of a cloud that's rotating. As it rotates, like the skater, closes in their arms. Well, this gravitationally, all this gas comes together and forms eventually this ball. This is the hypothesis, the nebular hypothesis. And they say this is how our sun formed. I have no problem with stars. Okay, I have no problem that that's how the sun could have formed. I think it could have been a big giant cloud of gas that rotates because of gravity. The gravity pulls every atom inwards and eventually condenses into this ball we call the sun, and then it continues through billions of years to compress and create light like our sun does. That's different than a rocky planet like the Earth, Venus, Mercury, Mars, Pluto, or any of the small one, like you take Ceres, which is the largest asteroid out there. It's a ball. It looks like this. Okay? It looks like a perfect ball if you look at it. And I'm saying anything that is a perfect ball out there was a sun, was a star. Okay, and what you'll notice that, for example, the Earth is differentiated. It's got all these different layers, and it goes from the more heavy elements towards the center to the lighter ones on the outside, to the point where you get to the gases on the outside, nitrogen, oxygen. That's what our air is made out of. What am I describing? A star. In the center, it's heavy, and the outside, it got silicon and eventually oxygen and so on. And when you look at all these round planets out there, or round objects, we'll call them celestial objects because Ceres is an asteroid, but a lot of them are differentiated, and again, they're differentiated in the right way. They've got the heavy elements on the inside and the lighter ones on the outside. And then why are they so round? Well, it was gravitationally chiseled. Okay, it was compressed. That's why it ends up as a round ball.
Radially
Yeah,
compressed.
yeah, that's the only way you can do it. So anything that's round out there was a star. Now, in the case of Jupiter, it could have been the nebular hypothesis because it's still a gas ball. That's all it is. But what you got to explain is not the gas ball, which is the one we're always fascinated with. You got to explain, for example, the Galilean moons. Why is Io? Why is Europa? Why are those rocky planets? If Jupiter was part of that cloud of gas that formed the sun, why do the moons of Jupiter, why are they rocky if they're at the same distance from the sun? You would think that everything either turns into gas or everything turns into little balls. And here you have these moons. They're rocky moons like our moon, like Mercury. All these are rocky planets or things, celestial objects. And they're next to this gaseous planet called Jupiter. Same thing for Saturn. Same thing for Uranus and Neptune. So that's when people talk about the nebular hypothesis, I want to go to the moons of Jupiter or to Saturn.
Jupiter's gaseous, but the moons are rocky.
Please tell me why. And they're at the same distance from the sun. So, in my opinion, Jupiter could have formed from a nebular hypothesis because it's still a star in formation and never will ignite. Probably it's too small. But what you got to explain, but you got to explain the rocky moons it's got. That's where I'm.
Maybe
saying.
Jupiter's our backup sun. When the sun explodes, we got Jupiter to turn into a sun.
Or we can run away to Jupiter. Okay, let's move on here. Another in the news this week, and this has to do with light bending X-ray echoes from behind a supermassive black hole.
What does the title even mean?
Well, it says that light is coming. They finally discovered for the first time. That's why it was in the news. Emissions from behind the black hole. They're saying that the black hole is throwing light from behind it, and we can't see behind it because we can't see through the black hole.
But the light curves around it.
Curves around and comes to and it comes all the way to our eyes. So they said that these emissions are from behind, and the reason they claim that that is the case is that the black hole is rotating. And so because it rotates, what happens is the front part, let's say it rotates from left to right. Okay, so from above it's rotating counterclockwise. Okay, we got that?
Yeah.
And so it's going like this, right? When it comes to you, it should be blue shifted. Whatever is coming to you, the light should be blue shifted. And when it goes away, it should be red shifted.
So the
and that's
left side's coming towards us and the right side's going away from us?
And so they say it's the light from behind because the thing is rotating, and as it comes, you have this, and they know it's light from the black hole, they say, because as it comes towards you, it's blue shifted, and the one that's going away is red shifted. That's how they figure that out. And so the big news was black hole is emitting light from behind. Now, this contradicts everything we had from the 60s on black holes, that nothing escapes a black hole, especially light, because everything at the event horizon is sucked inwards at the speed of light, I guess, or greater. I don't know. Maybe it breaks the
Depends
laws.
on who you ask.
Yeah. But the point is, at least the speed of light. That's why they talk about escape velocity. Okay, the escape velocity is little c, and I know my friend Stephen Crothers has something to say about that. You can look up his work out there, and he'll tell you that it's nonsense to talk about escape velocity out of the event horizon. I agree, but that's a long story. Anyways, the point here is that they discovered that light coming from behind the black hole, from its behind. And the question is, what is a black hole? Don't tell me about the light coming out of it, which already makes no sense, because that's why we call it a black hole, because nothing can escape. And then they came up with the Hawking radiation. The particle breaks into, the space particle breaks into positive and negative. One falls in, the other one comes out and reaches your eye. I don't know why that one doesn't fall in as well. So a lot of this nonsense that they have out there. But the point is, what is a black hole to begin with? It's a zero-dimensional singularity.
You don't know what a black hole is?
Yeah, I don't know. It's a zero-dimensional singularity surrounded by a concept known as an event horizon.
Is it a hole in space? Is it a sphere? What are we talking about?
Yeah, what are we talking about? That's
but essentially, what did they see? They saw blue shifted and red shifted.
Right, that's it. And they say they concluded from that.
But then we can, maybe, assuming that's correct, then we can conclude that something is spinning there.
Maybe. What if there's nothing spinning, and it's what I'm saying it is, which it has to do with the magnetic lines, threads
spinning through
through that region. Okay, and what you have in that region is gases. We can't see the gases from here. I mean, you can't detect that. But what you have is the magnetic lines of force, in this case, the threads going through those gases just at great speeds. You're talking about the galactic, could be from another star nearby also, and they're going right through that region, and that's what's sparking that region and giving you the impression that there's something there other than gases.
That's a nice word combination. Galactic magnetism. That sounds nice. That's a nice band name.